Welcome back, everyone. This next series of presentations will provide more detailed technical information about several critical components of the Peer CEA project. So would just like to remind you to please submit your questions. There's a Q&A button at the bottom of your Zoom screen. So without any further ado, we will now hear about the loading protocol selection, and this will be presented by Professor Farzin Zareian from UC Irvine. This loading protocol was developed for the experimental testing program. Farzin, please take it away.
Thank you very much, Grace, Janila, and everybody else on the call. I just want to make sure that everybody can hear me and I have control of the mouse.
Yes, we can hear you.
Yeah, okay. So good afternoon, everyone. I am a small part of this major effort, and what we did along with colleagues in working group 3.2, which includes myself, Chaoming Yuang, Tara Hutchinson, Brett Bozorgnia, and Silvia Mazzoni. We worked together to develop a loading protocol that folks in working group 4 can use to develop the data that is further down the line used for testing and analysis. So I think I have to use the mouse to move forward, yeah. So what I have for you is, well, why do we use loading protocols? What you see on the screen is a building on a cripple wall, and I don't know why this moved down. Okay. Probably is with the transitions. It's a building on a cripple wall, and at the middle of the screen, you see drift ratios. These are the different kind of a representative things, that kind of behavior that you see at the cripple wall, that eventually there's a transition from house supported on cripple walls, nothing happening on the left-hand side, all the way down to where the building will fall and collapse. Now, with this image, what I want to actually do is to start the conversation and say, why do we use the loading protocols? And there are three objectives. One is that you might want to do an evaluation of the behavior of your components, in this case, cripple walls, and check your analytical component models. This is what we actually did in this project. That was the intention of developing these loading protocols. At the same time, these loading protocols can be used to develop damage fragility curves, and later on do component quality control. The last two that I just mentioned, FEMA 461 has loading protocols for developing damage fragility curves on non-structural components. Or we hear about the SAG project and the pre-qualified connections. There are loading protocols that you can use to do component quality control. These are our suggestions for future work from where we are in the CEA project. But the intention that we had to developing these loading protocols was to make sure that our analytical models can capture the behavior of cripple walls from low level of damage all the way to collapse level, let's say. So with this in mind, we had a really large task order in front of us. These slide transitions are taking a little bit of a time to move forward. I need to be a bit mindful of that. So we imposed seismic demands on these cripple wall models that we had. We need to make sure that ground motions are representative of different locations in California, the work that Working Group 3.1 has done, and I wouldn't do much on that regard because Silvia is going to speak a lot about that task. Different soil types, different scenarios in terms of distance and magnitude, and the work that you're going to hear tomorrow from Dave and others on structural behavior. There's interaction between the cripple wall and the superstructure, different retrofits, different detailing. All of these should actually come to a single loading protocol that we decided to have for this project. And this takes me to the bullet number 2. A small number of quasi-static tests should represent the fate of all possible combinations of parameters affecting the component. Other loading protocols that has been used in the past for wood frame buildings, which I'm going to show a few of them, usually use 2 tests, but we had the opportunity, or we actually did the work that everything can be done with a single test for each setting. And ultimately, the last bullet, the loading sequence should allow for the assessment of component behavior from at various stages, from very slight damage all the way to collapse. We did a good amount of literature survey for our work. And I hope, again, the next slide comes up. And there are 3 research in the past that really clearly speak to what we were doing. Number 1, the work happened at Stanford with Helmut Winkler and co-workers, that they developed a loading protocol for wood frame structures. This loading protocol was used by Chai, Hutchinson, and co-workers at Davis to look into the behavior of cripple walls. And the work that Chaoming Yuan did with Gatto on looking into the sensitivity of behavior of wood frame components to different aspects of loading protocols. All of these we looked at. What you see on the screen right now is the loading protocols that existed, and from top to bottom is the transition of in time. The SPD, or the sequential phase displacement project, something that happened at UCI a very long time ago. If you see it, look at this loading protocol, it has a lot of cycles. Basically, this loading protocol moved the mode of failure from the component to the fatigue of the nails, and the ISO, something that the folks in Switzerland built. The work that happened at Stanford with the Curie project, they come up with 2 loading protocols, as you can see. The bottom one, the near fault, and the standard, or later on they called it the ordinary loading protocol. This is our starting point. I would like to mention something about the work that Tara Hutchinson and Chai did at Davis. Their work showed that using the near fault loading protocol of the Curie one didn't change the results in terms of strength demand and displacement demand by much. There was mostly 10% difference. So this basically gives us the ammunition to focus mostly on a standard ordinary ground motion loading protocol and leave the near fault component to a later study if the need is. We're waiting for the next slide. So the parameters that we use for developing our loading protocols, we looked at 2 locations, Northridge, Oakland, 2 types of soil, 270 and 760 meter per second for VS30. We looked into 4 different hazard levels, from ordinary all the way up to the extreme levels, 72, 475,000 and 2475 years, and 2 types of finishes, stucco and wood siding. Later on, we sprinkled this major set of parameters with new models that were developed at Stanford to make sure that our loading protocol still captures, because if you think about it, it's like a circular approach. We developed the loading protocol, analytical models are checked, we need to bring back the loading, new analytical modeling to make sure that the loading protocol that we had still is represented. So with this, and without bothering you with further details, let me show you what we have in terms of our loading protocol and how it compares with the best before it, which was the work by Curie at Stanford University. The yellow line that you see is the loading protocol from their work. The vertical axis shows the relative amplitude. I have normalized this for our work, which is we're assuming that at 1% drift is the target, is the reference drift level that that we anchor our loading protocol. The horizontal axis shows the number of cycles. The only thing that we did, and we realized that it's a really good starting point, is that we removed the trailing cycles. If you look at this part of the screen where you see the middle where it says 0.4 on the loading protocol, after that you see that the black lines are continuing with the same amplitude of 0.4, whereas the yellow line drops. These are the trailing cycles in the Curie loading protocol, which we really thought that it's not needed for our loading protocol. We also continued our loading protocol all the way up to the level that there is a major drop in the strength demand. And this is shown in this slide with the orange line. is the same. Vertical axis and the horizontal axis are the same, just the range of the vertical axis changed, and we have 2 cycles for every increase in the drift limit. Later on, after we saw the results of the test at San Diego, we decided that maybe 1 cycle increase for each, 1 cycle for each increase in amplitude is enough. Now with this, let's take a look at the next slide, which we're waiting for it. Now in this one, coming out of the normalized domain and looking at testing the loading protocol for the 2-foot wall, vertical axis displacement, horizontal axis number of loading steps. This was given to the folks in working group 4 to do their 2-foot cripple wall testing. Some might ask, what was the process that you used to develop your loading protocols? Well, in order to explain that process, I need to go through a little bit of a terminology. If you remember the previous slides, number of cycles, which 1 cycle is 1 up, 1 down, and the vertical axis is the movement that the actuator has. There is another way of presenting this plot, which actually lends itself to the process that we use to develop the loading protocol. The horizontal axis shows the step. It's basically every cycle becomes 2 steps, 1 push, 1 pull. Combination of a push and pull becomes a cycle. And the vertical axis in the bigger plot is the excursion from maximum to minimum movement. And these 2 are equivalent of each other. So we wanted to come up with statistics of this excursion cycle. And if we go with the long cycles, with the orange as this, with what we call it, the extended cycles, it shows itself with this gray line on the side. The process, I'm sure that Dave and folks from Stanford are going to show this slide tomorrow. This is the basis of the model that was used to develop the information for the result of our work. And I'm going to skip this one just to give you how the model looked and showing you the ground motions. There are 4 sets of ground motions. I want everyone to remember these color codes: blue, green, gray, red, representing 500,000 year and 2,500 year return period of our ground motions. This is just one spectra out of many that were used. Dashed line used the statistics of what was selected, and the solid line shows what was the target, shows the beauty of the work of working group 3.1 to give us a good set of ground motions. With this, and given that I don't have much time, I'm just going to go through finish the process, and I'm going to show you the results. We get these cycles of drift from applying the ground motions. We're going to count the excursion, and we're going to line them up. You might ask, what are these excursions? These are going up and down on this cycle. As you see, the oranges are going up and down on the history of the response, and eventually it's going to give us the counting excursion and then ordered excursion. And finally, we do statistics of 40 ground motions, and you're going to see these plots of 84 percentile and 50 percentile of the ordered excursions. We're going to put them on our target or suggested loading protocol. The way that you see the blue line is the result of one of the statistics that we do. And we're going to see if this suggested loading protocol makes sense. If it didn't make sense, we need to change the number of cycles to make sure that it is matching all of our work. Just to give you a little more feeling about the work that we did, this is the history for one of the 2-foot curple walls that we did with, this is retrofitted with horizontal siding. Northridge and Oakland, both results are in here. 2 directions of ground motions in X and Z. You can imagine that X and Z are the 2 horizontal directions, and ground motions representative of 270 and 760 meter per second soil type. As I mentioned earlier, horizontal axis number of steps, vertical axis drift ratio. The results for the low intensity set nicely matches the low drift ratios for us. As I go with the green color, and the yellow is our suggested, as I go with the green color, you will see that it nicely matches our suggested loading protocol. And if I go to blue, which is our gray, which is our 1,000-year return period, matches well. And eventually with the 2,500-year, the extreme levels of our suggested loading protocol. Taking these clouds away from the slide to give you a better feeling about what we have. You see that all of them nicely ordered, 72, 475,000 and 24,750, 22,475 years, and different levels of excursions. This, all of it, and there was a lot of artwork that we did, eventually led to the loading protocol that I showed earlier for the 2-foot, for 4-foot, or for 6-foot wall that can be used for, by the San Diego group to do the cripple wall testing. I know that it might have been 100 mile per hour presentation for you, but that's all I had. Thank you very much for listening to me, and I'll take questions if you guys have any. Thank you so much.
Thank you, Farzin. That was a lightning round. I would like to ask people if you do have questions or if you need some elaboration on the material, to please submit it in the Q&A at the bottom of your screen. Thank you. Now we'll hear about the experimental testing program, which was conducted at UC San Diego and UC Berkeley. And so this program will be described in more detail. And quantified data of the behavior of unretrofitted and retrofitted specimens will be presented by Professor Tara Hutchinson of UC San Diego and Kelly Cobeen, who's Associate Principal at Janney Elstner Associates. The testing data was critical to validate the analytical modeling and analysis efforts of our project. Tara, take it away.
Thank you so much, Grace. Make sure I control. Okay. Thank you so much, Grace, and thank you to the CEA for inviting, obviously, the group to this, the wonderful lead-ins by our colleagues Yousef and Grace and Evan and others. And of course, Farzin set the tone for the discussion regarding the experimental program with his work with our colleague Xiaoming Wang on laying the foundation to provide a protocol for this program, which was used, I should mention, throughout both efforts, UC Berkeley led by Cobeen, and at UC San Diego, work that myself and Brandon Schiller, PhD student, have conducted there. So, okay, the speed is decent. In this discussion, I'll try to give you a flavor for the plan and the objectives of the program, and then a perspective on the UC San Diego contribution to testing small cripple wall components. And then Kelly will take over and talk about the UC Berkeley large component testing and try to wrap it up with some findings. It's been a pleasure to work with this group, I should say. Kelly and I corralled folks, but we had terrific input from a number of folks, including those working on the ground, such as Brandon Schiller, Brett Lazindia, my colleague Gilberto Mosqueda, Xiaoming Wang, Figadetti, and Thor Madison, as well as John Vanderlyn. And as well, we had a project advisory team with contributions to a number of the facets of this work. So we really want to extend thanks to them for their efforts on behalf of the entire working group 4. So it's already been mentioned, of course, what is a cripple wall, but for the purposes of terminology, we understand that it is that sub element rising from the foundation to the underfloor, as shown nicely in the depiction here of this older 2-story dwelling. Why retrofit the cripple wall is self-evident, I suppose, in this photographic sequence from the Napa and Santa Cruz events. The catastrophic damage to the superstructure due to the loss of stability of the cripple wall is well found and well known under seismic events. So as Kelly laid out from the work of the ATC 110 project, nowadays the strategy for retrofitting the cripple wall is to come in the underlane and primarily place plywood sheathing, follow the load path, and implement clip and bracing elements, and potentially augment the load transfer at the sill as well. But some of that has not observed prevalence in experimental literature. So in that regard, the purposes of this program, both at Berkeley and at UC San Diego, was to fill the gaps in the component test record in the literature, develop some hysteretic behavioral models which could be used by Working Group 5, and I believe Dave Welch and Greg Deerline will speak tomorrow about their nonlinear response history analysis. Collect data on damage as it progressed to be considered by the fragility damage functions. And you saw some pictures of that from Evan's presentation earlier to lay the foundation for that discussion tomorrow. So our program was two-faceted, as noted. At UC San Diego, Brandon Schiller and myself worked on small cripple wall components, wide variety of them, and I'll focus this short discussion on that facet, and then Kelly will take over. And Kelly and Vahid Madavifar worked on a variety of extensions of that, not only large components, but as well load path connections, bracing of materials and bracing of materials in occupied stories. And she'll share with you some of her findings there. Now we get a little bit of a lag that Farzin observed. So, okay. The goal of the UC San Diego experimental program is really, of course, to understand the behavior of cripple walls as a small component in their own right, focusing only on those as a component. In the end, we performed 28 quasi-static reverse cyclic tests of these components, incremental loading steps with negligible inertial load following the protocol that Farzin and Xiaoming laid out for us. The variables we focused on were largely derived work of Working Group 2, and Evan spoke about that this morning, laying the foundation for the type of, in particular, finishes that existed in the eras derived from their group as prior to 1945, about 45 to 55, and beyond 55 up until about the 1970 era. This included, of course, some variations in exterior finish type. We also looked into the issue of boundary conditions, which ended up actually occupying at least one of our 4 phases of testing, as well as anchorage type. To our knowledge, although there are other issues existing in retrofit, cripple wall height, those items here in green effectively had very little study in the literature. So we felt that we could focus our time and our precious resources on those 4 in particular. Oh, the lag is appreciable. I have to learn from you, Farzin. Apologize for that. I didn't expect that. I didn't notice that in the earlier discussion. So the outcome of this program from UC San Diego's perspective, okay, there we go, was really to develop force displacement hysteresis of the cripple wall as a component, eyeing in on the key parameters of strength, drift at strength, and as well the service level drift and strength. We attempted to keep track of the damage as it evolved during the cyclic testing. So as an outcome, a useful outcome for the community, we have I would say a very rich image data set correlating that damage to drift amplitude, and Grace shared with you where all of that data is to be posted. We did our due diligence to try to organize that data, as well as an extensive video database. I'll show you one video in this, we'll see how it goes, but there are so many more that have been composed, and I want to thank a number of undergraduate students that worked with Brandon, as well as Brandon himself, who worked on that task. We have, I believe, some very useful video footage from these small component tests. In the end, you know, it is useful, of course, to cross-compare key parameters, finish type, retrofit, the effective retrofit and the effective boundary condition bubble to the highest priority in this particular effort. Okay, we'll just a little bit quicker here. Too many animations, I suppose. The exterior finish types, we categorize them roughly as wet exterior finishes and dry exterior finishes. Wet involve any overlaying of stucco. We considered stucco over horizontal sheathing. You'll see it in the upper left here as a sort of our baseline condition, stucco over diagonal sheathing, as well as plain stucco adhered to bare framing. Dry finishes involve things like horizontal siding over diagonal sheathing, and T111 wood structural panels. Retrofitting followed the plans that was near completion at the start of this program, namely the FEMA P 1100 retrofit guidelines that Kelly spoke about this morning, involved, of course, installing wood structural paneling. You can see some of the detailing here. We worked with folks in practice to get some guidelines in terms of blocking and nailing at anchorage, which would be ideally designed to detail the interior of the frame segment before the wood structural panel was installed. The only outlier to this was 111 in the case of retrofitting. The 1100 retrofit guidelines allows us to simply augment or enrich that paneling with additional nailing. And so we applied that same technique here to the retrofit of T111. I mentioned we looked at boundary conditions when this slide comes up. We looked at not only the top of well, we looked at it maybe from the top and the bottom boundary condition, let's say, and in the context of a cripple wall, the top being the interface between the top plate and the framing, which would naturally come up above. We sort of naively label them A, B, C. You can see the top boundary condition A is what we tested at UC Davis when I was there years ago. This was captured throughout the program. In fact, there's really no corner, let's say, per se, light furring, nailing, and simply a double top plate. There was some work done by my colleague Ding Wong and others, and Arnold, through as well a CEA project that looked at the validity of that type of detail with respect to capturing the continuity of the surrounding framing. And they suggest that a more robust nailing arrangement at a top plate, namely a triple top plate, that doesn't show this here. You're seeing the finish, the stucco finish face, but you can see that the dramatic difference in the wraparound of the stucco comparing this upper left figure and this lower figure. That's intended to emulate the continuity that would be present in the typical cripple wall. We also studied one other condition. I want to thank Brett Lazuni actually for this idea. He wanted us to take a look at if that continuity was even extended even further. So we call this boundary condition C, sort of a return wall that extended an additional bay beyond being a simple wraparound. I think is useful for this program to invade that issue. The dense furring nail arrangement, I should note here, was really to mimic the stucco continuity of the first floor, as mentioned. Not only the top boundary condition was modeled, but as well we investigated the bottom boundary condition. Okay, here it comes. And you can see the variability in the series of images here. Bottom boundary condition A up in the upper right, perhaps not as common. The sheathing, or excuse me, bottom boundary condition A. Up in the upper left, the stucco was outboard, the sheathing was bearing on the foundation. It's one configuration we observed in practice. Bottom boundary condition B, the finish bearing on the foundation, not as common, obviously, but still a useful, let's say, upper bound where all of that bearing of the wall coming down during the shearing, during the imposed shearing is actually captured. That's perhaps a very extreme condition. We as well looked at boundary condition, what we call boundary condition C, all finishes outboard. This is akin to the Curie test. All of the finishes, you can see just the edge of the foundation there. And this is for horizontal siding case, obviously, but that was also emulated in some of the wet condition stucco configurations. And then we also extended the tail of the stucco down onto the footing for a few cases so we could assess the ramification of that more natural condition. One may consider that in the event of an older home that would effectively be deteriorated, and you would likely have no adherence as you would in this upper left image. We felt it would be useful for our testing program to investigate that issue. Here's some photographs of the test setup. The on the left and the lower right show two foot wall configurations. Column on the left articulate the heavy vertical load configuration where we imposed gravity load on the order of 400 pounds per lineal foot, which was intended to emulate a two-story flooring configuration, in contrast to a plate style assembly on atop the steel transfer beam in the lower right, which was intended to emulate what we refer to as a light vertical load, which was intended to emulate a single story light framing configuration. We also looked at, for the first time, looked at very tall cripple walls. And here you see a stucco wall standing upwards of 6 feet. I should mention all of these specimens were of a consistent length of 12 feet. So that effectively meant an aspect ratio of 1 to 2 in this configuration. Okay. Okay. Let's see if how successful this video is. As I mentioned, we have a number of, I think, very useful videos in the repository that are will be accessible to everyone. Want to thank Dr. Chris Latham. He actually edits these particular videos, which involve harmonizing the webcam views that we broadcast during the testing. If it ever gets there, let's see. Sure, this is going to work. There we go. On my side, I can see it. Hopefully, other can. He harmonizes these videos with the webcam views. In this case, we set up webcams to look at the interior and the exterior of the cripple wall, and with the measured shear force versus drift and drift versus pseudo time on the left and right, respectively. You can see during the low amplitude cycles, I'm not sure if you can read the x-axis of this, but this is within the serviceability ranges. You can envision the specimen is still retained as more or less a in its quasi-linear state. You can see some hysteresis develop, a relatively pinch type of behavior. You can envision that strength is approaching now. You can see a nominal amount of sliding of the specimen. We saw that for until one overcomes and attains bracing of the bolts. There's a nominal gap, of course. And now you can see strength has been achieved and a deterioration accomplished in the specimen. If I move forward, okay. So let me try to show you some results here. The series of snapshots of, oh boy. Oops, once you get it up, your slides up, doesn't work out too well. Sorry about that. Farzin was better with his timing. Okay, I can see the slide effects of boundary condition. These are the envelopes of a series of 2 foot tall specimens. The family on the right shows the top boundary condition, the implication of varying the top boundary condition. The family on the left shows the implication of the bottom boundary condition. And you can see that the wall return, if we look at the upper right, the wall return and the corner baseline specimen more or less track each other, which is good news. Corner baseline condition was carried through. We decided was carried through to the remainder of the program. You can see that no corner, let's say, or no physical intent to off continuity in the spin results in a dramatic reduction in the strength. This was akin to the Curie type of details that we tested at UC Davis earlier. It certainly meant that we were capturing the continuity in the wall return and the above flooring a bit better by going that extra leg with the detailing. In terms of the bottom boundary condition, with the finishes bearing, we see a very large strength compared to other configurations. That's very rare, I would say, probably condition in practice. With the finishes outboard, there's nominally consistency between finishes outboard and finished stucco only outboard. There's a slight increase in the drift strength when the stucco is placed outboard, and the bearing of the sheathing intends to separate, let's say, the sheathing and the stucco as a finished unit, so that suppresses effectively and allows a slight bit more drift drift at strength in that configuration. Some additional results here. Let me get them all up. Comparing a variety of fishes. One thing to mention is that this pair of plots in the left and the right respectively articulate the envelopes in terms of lateral forces drift, comparing relative drift and global drift in the left and right respectively. And it highlights the fact that we did see sliding of the sill relative to the foundation due to the fact that these were the existing specimens, unretrofitted specimens, were fairly lightly anchored. I won't go through all of these details as we've got a strong family of reports, I think, which attempt to document all of this, but some useful remarks when cross-comparing these various finishes. Horizontal siding placed over diagonal sheathing, for example, tended to be one of our strongest specimens, and tended to, I should mention these are largely the dry specimens with a handful of stucco specimens sprinkled in. But this diagonal sheathing tended to be a fairly asymmetric type of behavior due to the opening and closing, or sort of breathing of the sheathing itself. As you can imagine, the bearing and the coming together of the sheathing element provided that additional strength. And so you can see that you observe up to 20 kips and downwards of 12 kips in the pull and the push direction, or the closure and the opening direction respectively. The softest, let's say, or weakest specimen amongst the family of specimens tested at the family of finishes were these horizontal siding only finished specimens. So a dramatic difference when you compare horizontal overlaying with diagonal sheathing to horizontal siding in its own right. We'll look at some damage photos in a minute, and you can see why that specimen. You can probably imagine the thinner finish, of course, as a substrate, but as well the fewer nails and the stacking of that lapped configuration siding all contribute to its relative soft type of response. Okay, the effect of retrofit was clearly something quite important to investigate experimentally, as we noted in the beginning. So what you see here on the upper row, on the topmost row of specimens, are 2-foot tall specimens, their global hysteretic response. On the lower row of specimens, their 6-foot tall response of a specimen response in terms of global lateral force and relative drift, in this case for each of these plots. Consistently for each of these, we're showing blue traces are retrofitted specimens, the red are the existing or unretrofitted specimens. And these are shown for a variety of different finishes, exterior finishes, horizontal siding, the first column, and stucco in the second column. These were the most common, let's say, pairs that we had decided were of highest priority. The horizontal siding being the softest specimens, you can see a huge increase due to the increase in strength and stiffness, and even deformation capacity due to the presence of the retrofit. Clearly the mode of failure is dramatically modified and is focused on damage to the interior plywood, which has been placed. And that was common to even the taller specimens. Again, a dramatic increase in strength for the horizontal siding specimen that was retrofitted. But that was not remiss and equally beneficial in the situation where stucco only, presumably weak stucco only exterior finish is present on the cripple wall component. And so you can see upwards of about a 3-fold increase in strength and nominally as well, an increase in the drift capacity as well, not as significant as that in the horizontal siding case, but still quite beneficial. We've printed these in terms of, looked at these numbers a variety of ways. You can look at them per lineal foot. You can look at them in bar charts. Bar charts ever come up? No, maybe not. Bar charts were supposed to come up. These bar charts, if they ever come up, articulate the percent increase in peak lateral strength for the families of like specimen. In other words, in the event that a 2-foot stucco over horizontal siding specimen is retrofit, what type of increase in terms of push and pull, since we have the benefit of understanding the strength in both directions, does one observe? We can see that that strength increase is on the order of 200 to 300% or so for almost all finish types, existing finish types, and it's consistent across 2-foot tall specimens and 6-foot tall specimens. And as we saw in the envelopes in the hysteresis, it's most dramatic in the case of horizontal only specimens, where upwards of 1,000 to 2,000% increases, very dramatic increases in strength is observed. Okay, I'll end with a couple of photographs. As mentioned, we did our level best to, I'll just click all the way through, then speak. So we're so delayed on reaction here. We are last, actually, great thanks to John Ostras, who guided us on the importance of collecting careful damage evolution photos at even the very low, what we might construe as service level drift amplitudes on the order of 1.4% drift or less. Certainly helps educate us on the damage scenario for various finish types under the state of the specimen, really still within its quasi-linear type of behavior. You can see very minimal damage even occurring on the retrofitted specimens, minor rotation of the nail, minor tearing of the nailing at even T111, a nominal closure of the diagonal sheathing if we're in the compressive direction, and reversal and updating and opening of the diagonal sheathing, still observant, sufficiently observant. Stucco corners, observing some splitting cracks and some tensile cracks around the continuous end elements of the specimens. Generally, little to no damage on the stucco face as it moves more or less rigidly with the specimen. In contrast, at strength of the specimen, oftentimes an express damage at the superficial face of the stucco, quite significant damage to the stucco corners, very visible, let's say quarter size or greater opening of the diagonal sheathing, a stair stepping type of pattern. You can see the red chalk marks that we placed for initial reference in the horizontal siding case. You can see that this stair stepping, an indication of the rotation and withdrawal active in the movement of the horizontal siding. You can just see in the T1 retrofit application case for this lower right figure, the rotation of the single 4-foot panels as the stair step is evident, the interface between those panels. And appreciable damage in the case of retrofit, as one would expect, to the fasteners, incipient pull out, and in some cases pull through, and crushing at the end of the plywood as it bears to the flat 2x at the end of the specimen and at the sill plate location. You can see the skirt style crushing occurring here. Oh, it's almost painful. Okay. Finally, useful to understand almost the residual damage state at a significant post-peak reduction of the specimen's strength. And here's a series of photographs articulating almost the final state of damage to the stucco finished specimen in the middle here, the 6-foot cripple wall with a retrofit, the Gordian style, and full tearing of all but about 20% of the nailing at the top sill in this elevation and isometric view to the left and lower left. You can see that the plywood is pulled outward under an extreme and low strength condition, complete crushing of the diagonal sheathing, complete gap closure, and we even saw some splitting of these boards, and a very expressed at very large deformation stair stepping of the horizontal siding. So I believe from my side, this is my last slide, and I don't have a concluding slide because I'm happy to just pass the docket to Kelly and remind us all that, you know, now from this data set, I believe we have some extremely useful information regarding both the existing and retrofitted cripple walls behavior in terms of force displacement, damage, evolution, and cross comparison of some of these important variables. All of this was intended to support the validation of numerical models, which David Welch and Greg Deerline will speak about tomorrow. They did a marvelous job actually tag teaming with us along the way and validating their models. And so we're really happy that it was used in real time effectively. So with that, I'll pass it on to Kelly.
Thank you very much, Tara, and I appreciate it. And hopefully everybody appreciates an awful lot of very, very good testing that happened at UC San Diego in order to feed very important information into the project, and really information that has been archived and will be useful for a very long time. So you've already seen this slide, and I just wanted to quickly mention Vahid Madavafar, a postdoc that worked with me at UC Berkeley on the testing, and also the wonderful folks at the UC Berkeley Structures Lab. The testing that was done at UC Berkeley was rather different in nature, although it was very much matched with what was happening in UC San Diego, especially for the group A. Tara had mentioned that we were trying to fill prioritized gaps in the test record in order to provide the Stanford numerical modeling group the best information possible to evaluate the cripple wall and the superstructure in both the pre-retrofit and the post-retrofit condition. And so the testing that happened at UC Berkeley was across a few different types of categories. And so we've got testing group A cripple walls, very much paired with what Tara was talking about at UC San Diego. Testing group B looked at load path connectors and tried to determine whether or not the load path connectors specified in FEMA P1100 could develop the full capacity of the retrofitted cripple wall, and we'll talk about why. And then testing group C was looking at materials in the occupied stories, and there were a few important combinations of materials for which the test data was missing, and so they set out to fill some of those gaps. So why did we do large component testing? And Tara talked a little bit about there being some previous testing that was done by Arnold and others at UC San Diego as part of a Curie CEA project that actually was done about the same time, and I believe in conjunction with the older assessment and repair guidelines that Morgan was talking about this morning. So they had gone and they had done some testing of walls that had stucco on one side and gypboard on the other. And they had found that the boundary conditions of that test, in exactly the way that Tara was talking about, had a huge impact on the outcome of the test. And so particularly for stucco and other materials with continuity, we knew that boundary conditions were incredibly important and could easily maybe double the capacity and drastically change the displacement at peak capacity and beyond. And so we wanted to go to large component testing that would, in as much as possible within a component test, have boundary conditions representative of the final structure. And so you see a photo here of the test that we built, actually two of these, one with retrofit and one without, in order to test cripple walls in this not quite full building, but almost full building kind of configuration. And what we got out of that was that we got the continuity of the stucco around the corners in this 4 foot by 20 foot plan building configuration. We got the continuity of the stucco from the cripple wall up into the superstructure, and we could get some idea of what that might do to change the behavior of the cripple wall stucco. And in addition, we ran the stucco down the face of the foundation. And if you go look at older stucco buildings that were built maybe before, even up into the 50s and beyond, you'll see that the stucco that's applied on the exterior runs right down the face and below grade at the perimeter of the house. And so it was very important for the stucco, and we carried the same concept over to the other testing that we were doing. And so I'm gonna go through and just show a few photos and a little bit of data and talk quickly through the different tests that we were looking at. But this is our three-dimensional large component structure that we did for the cripple wall testing with and without retrofit that you see right here. And it has the stucco run down the face of the foundation. Tara has already showed you marvelous graphs of with and without retrofit superimposed. And this is following along exactly the same pattern. And we were interested over the entire range of drift ratios was really the way we imposed the loading protocol that Farzin had come up with. They were all of interest. We weren't focused on peak or any single. And what you see here, the red is without retrofit and the blue is with. We get a significant increase in peak strength. We get a significant increase in the stiffness. We get this incredible toughness that allows us to cycle over and over and over again with the retrofit out to very large drift levels. And it just hangs in there and continues to perform well and very slowly reduces strength in a very well-behaved fashion. And so we were extremely happy with the kind of behavior we got. The other thing that I should note is that both with and without retrofit, we did a final monotonic push out to 40% drift. And the capacity was low, but it actually remained stable and functional out to 40% drift ratio, which is sort of off the charts as far as any prior testing. Just like what Tara was showing, a whole lot of the behavior that we were tracking was cracking that tend to focus around the corners. And if you think about how that wood frame stud cripple wall underneath wants to deform, in order to deform, it really does have to damage that corner. And so we tracked it across all kinds of different drift ratios. This isn't quite as fancy as the video that Tara had, but if you look in the upper right, you can see where you are in the hysteresis curve overall as you look at some of these photos. At 3% drift, the stucco that was run down the foundation popped. There was a large popping noise, and suddenly we could push a card up between the foundation and the stucco above. And after that point, the capacity started to step down fairly significantly. As we moved along, we really did beat up those corners, and we started to get the stucco flaring out like a skirt away from the framing. And eventually the stucco was completely detached, and we had left over horizontal wood sheathing underneath that gave us residual capacity. So we stepped through that. The retrofit you see here behaved very well, and our load path connectors and things really did support it out to the very end. We had a surprise failure, if you will, of the retrofitted cripple wall in the very end. In the end, we had a double top plate, and we had the nailing staggered between the two top plates. And we actually got a slip plane between the upper and lower top plate. And eventually we just shoved the diaphragm off of the cripple wall in its entirety. And so that was the very final push. We came to the conclusion it happened because the nails had been staggered between the upper and lower top plate. And we actually found out in time to go back to the ATC 110 FEMA P1100 and talked to that group about getting all of the nails put in the upper top plate in order to eliminate that failure mode. Moving along, specimen B1 was looking at the load path connectors. And the idea here is that with shorter cripple walls, particularly 2 feet and less than height, an awful lot of the connectors are not anchor bolts, but they are instead proprietary connectors. And so you will see in this photo shiny plates at 4 places along the foundation, and those are commercially available proprietary retrofit plates that attach the shear wall to the foundation and are out there in many, many cripple walls. In addition, there were angle clips at the top. And this is actually a wall that has a horizontal wood siding on the interior face and the retrofit on the exterior face. And you can see the little graphic showing on the left-hand side the pre-retrofit condition, and on the right-hand side with retrofit, and sort of the condition that we were emulating with the test. Hysteresis showing here, and we had a very high peak capacity, getting up to 1,500 pounds per linear foot for a fairly modest retrofit of the wall. And it performed very well. And once again, we had residual capacity out to absolutely huge drift levels. This one got tested to somewhere in excess of 30% drift and still had capacity. And that was something that was talked about in Peng's presentation when he talked about residual drift turning out to be a very important numerical modeling parameter to capture. Here you see look at 3% drift for these tests, and we were starting to get things prying up from the foundation and moving here and there. 3% drift, we started getting ripping of the building paper that was between the framing and the horizontal wood siding on the back side of this specimen. 6% drift, we started to see very obvious slip and things like that. We went up to about 15% cyclically on this. And at that point, the plywood was really fairly substantially detached from the surrounding framing. It was only sort of nominally held in place at that point. But we still got further drift, and you can see it's still nailed along the bottom in this particular sheet, but free on the top. And sometimes it was nailed on the top and free on the bottom. But we basically got every single bit of benefit we could out of that retrofit. And in the end, the proprietary connectors were still absolutely golden. There was very little sign of deformation and no sign whatsoever of degradation of them. And so that worked out really well. The last two specimens were the superstructure, and C1 was horizontal wood siding on the exterior, and it was plaster on wood lath on the interior. And you can see the bottom right figure showing the bottom condition we were emulating on the left-hand side and the actual constructed condition on the right-hand side. And the bottom plate in this case was nailed down to a wood nailer. So it wasn't directly anchor bolted down. The fastening of the bottom was by nails. And that happens fairly commonly if you have a stem wall condition. This is the hysteresis that we get out of this, and we've got a peak capacity of about 440 pounds per linear foot that you can see as the peaks there. That what you're seeing is the strength and stiffness of the plaster, and then the plaster starts degrading. But as it degrades, you get a huge amount of residual capacity retained out to something on the order of 17% drift. And to have it retain that capacity over that period of time is fairly amazing. We got a surprise the very, very first loading cycle that we did at 0.2% drift. First time we pushed it, there were huge pops, and we started to get buckling and delamination of the plaster on the interior. We had no idea that it would give out that soon. By 0.6% drift, we were starting to get very noticeable spalling. We see grace there. By 1.4% drift, we were getting large sections of the plaster on the interior falling off. And by 2% drift, which is pretty early on when we went up to about 17, we had just piles of plaster on the interior. But the plaster keys between each of those lath boards stayed in place, and we came to the conclusion that they were a good part of the residual capacity. They were still giving us capacity out of the wood lath and the keys acting together. There's 15% drift and fairly extreme, and we started seeing some damage to the exterior wood siding at that point. I think up to that point or not far before it had been really doing just fine. The last one that we did is plywood siding exterior and gypboard interior, and this is a T111 pattern siding. Huge amount of use of that starting in the 60s and going through the 80s. Lots and lots of houses out there constructed with it. We had a misinstallation, if you will, that's very common out in the building stock. At each of the vertical joints, the lower sheet was held in place by the upper sheet that was nailed. And so we didn't get both sheets at the abutting edges nailed. We only got one. And so that's much less than you would do if you were actually trying to use that as a shear wall. We see the hysteresis here, and we got up to about 820 pounds per linear foot. And we spent a lot of time tracking gypboard damage on the interior initially. And then we started to see the T111 siding rotate and offsets occur vertically. Eventually this failed because we pulled the nailed base plate off of the wood nailer that was bolted to the foundation. As we moved through, we actually withdrew all of the nails, and you had the nails being lifted up and then pushed horizontally. So it was a combined tension and shear failure. Eventually the walls walked off of the base, and we had to chain them back in order to continue safely testing the specimen. And this really only made it up to 6% drift. And at that point, we started shoving the walls back and forth across the base and crushing the siding, and it was in fairly bad shape. So I've got just a couple of minutes left, and I'm going to give just a few select highlights of findings that we had out of this. Small to large comparison. We did the large in order to find out what the outcome was with the boundary conditions as close to the full complete dwelling as we could. And there is an entire report in the peer report series that goes through this comparison in great detail. So if you're interested, please take a look at that. And we draw various conclusions about which of the small component tests both best matched the outcome of the large component test, and how all of them fell in sort of a range of upper bound to lower bound. The increased strength with retrofit was significant across both the small and large. Increase in deformation capacity occurred in almost all of the cripple walls, with one notable exception. Retrofit cripple walls experience less damage than those without retrofit, even when they're just loaded to the same drift ratio. When we compared the damage at 1.4% drift for retrofit versus not, the retrofit damage was always less. The drift ratios at peak capacity are higher in cripple walls than full story walls. The drift ratios that we're seeing here are much, much higher than the kind of peak drift ratios we've seen in full wall tests below. The damage was generally similar in character, but the locations of damage changed between the small and large. I think we've already seen a huge amount about the benefit of retrofit. Its peak capacity, its stiffness, it is ability to withstand lots of cycles and dissipate lots of energy. There are just a whole variety of things that improve dramatically when you go through the retrofit. And I think some of what we were seeing from Evan speaks to what the outcome of that is. Deformation capacity, the post-peak residual capacity is hugely important to the numerical modeling. And we certainly saw across all of the specimens that they retained capacity out to very, very large drift ratios. And some of the tests up to 40%, which is amazing. These figures were put together to compare the large component specimens that you see in the blue lines to the small component specimens with a variety of different boundary conditions, because we were looking at boundary conditions and their effects. And so the left-hand side is without retrofit and the right-hand side is with retrofit. One of the things that I'll talk about here, while there's lots we could get into, we're seeing dramatically different behavior, and that different behavior leads to very different numerical modeling. And so this created a whole lot of information for the Stanford team to sort through when they were trying to figure out how to approach the numerical modeling. One last thing I'd like to point out in terms of deformation capacity. This is specimens C1 and C2. So these are our superstructures, and the one on the upper left is horizontal wood siding exterior and plaster on wood lath interior, and that amazing retention of the post-peak capacity that we see. The one on the right is C2, that was the siding and the gypboard that really failed by pulling it off the base and really was no longer a functional system at 6% drift, or maybe before that if it hadn't been restrained. And this kind of challenges our traditional thoughts about what's brittle material and what's ductile material. Because once we're not just looking at the peak, but we're looking at all of this post-peak residual, plaster on wood lath that we would normally think of as very brittle actually has incredibly ductile behavior and retains strength out to huge deformations. Whereas with the siding, the plywood siding, we would normally think as being like a plywood shear wall and a more ductile product. We exhausted our displacement capacity well before it was exhausted with the plaster on wood lath material. One last slide here, the commercially available connectors, we were able to see that if they were selected in accordance with FEMA P1100, that they really did develop the capacity and meet the intent of FEMA P1100 without noticeable degradation. Thank you very much, and I will now turn it back over to Grace.
Great. Thank you so much, Kelly and Tara. A lot of rich data that came from this testing program. And as Tara and Kelly mentioned, it is all posted on the project webpage, and we can provide that information to you again later. At this point, let's see, to our attendees, if you have any questions or if you need elaboration, please do submit your questions in the Q&A button at the bottom of your Zoom screen, and we'll address them at the end of this session. Now I'd like to introduce Silvia Mazzoni, who's a project scientist at UCLA. She will outline the seismic hazard ground motion selection process. And again, this effort also fed into the modeling and analysis efforts for the project. Silvia.
Thank you. You can hear me all good? Okay, perfect. Thank you for your attention. I love the last two presentations and the previous ones. It was nice to go back to the lab for a little bit, even though it was virtual. I'm going to bring us back to loading protocols and ground motions for analysis. And so what we did in our working group is we performed a seismic hazard analysis and selected ground motions for structural analysis for the working group at Stanford. Okay. This is a busy slide, is the only busy slide I have, but I really wanted to show you the importance of all the different components that we had to take into account when selecting the ground motions for analysis. It wasn't a single case for a single building at a single site. We were really trying to, develop ground motions that were representative of the scope of the project. The good thing is early on, we met with pretty much all the working groups to discuss the different considerations that we needed to make, and even the technical advisory team was there. And that was a really great initial step to resolve a lot of the issues and questions. To make sure that we covered all of California, we selected 10 sites. As you've heard in the other talks, those were narrowed down based on the representative shape of the hazard and shape of the spectra, to minimize the amount of work that the analysis group had to do. But we really wanted to start broad, and we want to represent both the diverse seismicity of California, both Northern California, Central California, and Southern California, as well as important population centers. And so that's where we came down to only 10 sites. For each site, we wanted to look at 2 site conditions. Each one of these sites, as much as we had to pick a point, a specific location, where we picked actually City Hall for all of them but one place, we didn't want to use just a site condition at that site. So we developed ground motion suites for 2 different site conditions. One for a stiff soil at 760 meters per second for the shear wave velocity, because that's just a typical reference type that you use in ground motion analysis. And then we looked at a softer soil condition at 270 meters per second, which is much more representative of the actual site conditions at most of the residential areas where you would find these types of buildings. So it was very much of a picking points, but then being able to smear the data so that we were very much representative of all of California. For each site and site conditions, we narrowed it down to only 40 ground motion suites per site. We wanted a good number that was sufficient to give us some good statistics, be able to meet both the mean and a variability in the ground motions, but we really didn't want to overwhelm the analysis group. So 40 ground motions was the number that we agreed on with the team. Then we had to choose the return periods for the analysis because we had to give them hazard consistent ground motions for analysis. And so coming in from the building code, we were looking, okay, well, 2,500 year return period, maybe we'll go all the way down to maybe 250. And that's when the modelers came in and had us bring it all the way down to 15-year return period. So we had a whole gamut of hazard from, earthquakes you get every other day to the rare ones. We had to also define a period range for ground motion selection. Building code will tell you, a specific range for your site and your building. And we wanted to have something wide enough that would cover whatever the period would be for the different model cases. We decided this early on when there wasn't even a structural model yet. So we looked at a range between 0.01 and 2 seconds. So we're in the shorter period range, or definitely not in the long period range. Initially, we were looking at developing ground motions for the uniform hazard spectrum, but in discussions with the analysis team, we were open to that. We developed a conditional mean spectrum and select a conditioning period for the conditional mean spectrum. By this point, the structural analysis group had given us a period, and we conditioned our spectra at 0.25. And we just ran it for this one single conditioning period. And so now for each site, we had 2 different types of target spectra. So the process, which I'm kind of putting into a little loop here, which kind of got loopy at some point, is that for each site condition and site location, we first performed a seismic hazard analysis. And then from there, we pulled out uniform hazard spectra for the different return periods with the deaggregation data, as well as for each target spectrum type, we had to define both the CMS and the UHS, and therefore define a mean and a variability of the ground motions about that mean. And we had different cases depending on whether you're using the UHS or the CMS. And I'll talk about that in a future slide. For each one of these cases, we selected 40 horizontal record pairs, horizontal ground motion record pairs. And these selections were based on the deaggregation. We tried to, we couldn't really be too specific for, looking at an individual site. So we used relatively broad scenarios or magnitude distant ranges for a ground motion so that we could cover an area of more of a city versus a single building location. We scaled the records we obtained the records from the NGA West 2 database, and we scaled them based on the target spectrum. And then we also looked at evaluating the pulse content of these ground motions. And I have a slide on that as well. So just to give you a little map of what's here, in red, you see the faults from the Yousef 3 fault source model that somebody else had already presented earlier. And just to kind of show you where our locations of the 10 different sites is. For the site, we've got 3 sites in Northern California, San Francisco, Oakland, and San Jose. And then we have 2 sites that represented the Central Valley as well as a lower seismicity. So we picked Sacramento and Bakersfield, mainly also because of their higher population density as well. Then for Southern California, we had 4 to 5 sites. The very last one is San Diego, because again, that's a large population center with a different seismicity from the LA Basin area. And then in LA, we wanted, such a wide area. We looked at the San Fernando Valley, LA, and Long Beach. But for San Fernando, we actually replaced it with Northridge. So for all these cities, we picked the location of the city hall. But for Northridge, I think we picked some important intersections since it's not a city itself. But we thought it was value to give a nod to Northridge. As I've already said before, for each one of these cases, we looked at 2 site classes, 270 and 760 meters per second. And here is the list of the return periods, as I've already mentioned, between 15.5 and 2,500 year return periods. So it's the whole gamut of ground motions, which makes for wonderful plots. The probabilistic seismic hazard analysis study was performed by Nick Greger and Linda Alatik because we really wanted state of the art. That was the mandate from CEA, is to really use the best science that we could. And so Nick and Linda are using the latest science, using the Yousef seismic source characterization with all the important characteristics that are associated with that. We used 4 NGA West 2 models, equally weighted. As you can see, we're missing the Idris ground motion model, mainly because that one doesn't apply to the 270 meters per second for the softer soil condition. And we wanted to have consistency between the 2 site conditions. So we decided to only use these 4 ground motion models, which is fine because 4 is better than less than that. We used the epistemic model developed by Linda Latique and Youngs in 2014. And as I've already stated, they gave us the data for 2 different site conditions. We took these data, and I have here just kind of give you an idea of what the two of the many sites that we looked at look like. So we've got in the top figure, we actually have Oakland and San Francisco. As you can see, the Oakland and San Francisco are in an interesting location because they're sandwiched between the Hayward Fault and the San Andreas Fault. So 2 significant faults and a whole bunch of faults that run in parallel on the other side. And you can see that's very different from the situation of Northridge down in the LA Basin, which is in itself is a location that we picked, is very much in the near field. But then you see that there's a lot of much smaller faults in some areas, and then there's some population areas that are not in the near field. And so this was a really important consideration as to what do we do? Do we represent these as near field sites because the one location is in that area? And so we decided to smear our ground motions to make sure that we included near field characteristics as much as we included not so near characteristics. Of course, LA, everything is in the near field. A figure on the bottom left compares the response vector, or the uniform hazard spectra for the 2 sites of Oakland and Northridge. Interestingly, if you look at them, I mean, these are even in a linear plot, you can see that there's relatively minor differences in the shape of the spectra and even the amplitude. But it was important to run all these cases and actually move forward in developing ground motions for all these different sites, because maybe small differences in the spectral shape could actually lead to differences in the structural model results. So it was important for us, it was easier to do everything at once, that we developed a wider set of ground motions than what was actually used. But it's interesting because we weren't just looking at the spectral shape, we also looked at the deaggregation. And this is a tricky figure because the distance bin, so what we're plotting here is Oakland and Northridge. So Oakland is on the left, Northridge is on the right. The top figure is for the softer site with a 475-year return period. And then the bottom figure has a stiffer soil condition with a 2,500-year return period, just to kind of give you a diversity or comparison of the 2. You can see that both sites are in a relatively near field, but the distribution of magnitudes is different between the 2 different sites. And so that does play into the ground motion selection, because not only do you pick magnitudes, but you also have distances and other characteristics. So we want to make sure that we were very academic about the exercise and we represented each site and give enough attention to each of these conditions. Which then, once we had decided on the sites and we've gotten the hazard data, we move forward in choosing a target for the ground motion suites. So we developed 2 suites of ground motions. Of course, each suite consisted of about 200 suites, depending on the different 10 sites and all the site conditions. But these 2 major subsets of ground motion selection, one was based using a UHS, the Uniform Hazard Spectrum, for the selection, and the other one is using the conditional mean spectrum as the target for the mean of each suite. Now, what really comes into play is what kind of variability do you have associated with these target spectra? We wanted something that was realistic and representative of what we wanted to do, but again, make it particular but not specific. So what we did is the process when you do a ground motion selection with the uniform hazard spectrum is you using uniform hazard spectrum as your target in a certain period range, but then you select the ground motions that have the best fit to your target spectrum in the mean. And so that by itself, so by the definition of selecting ground motions based on the mean square error, you lead to a ground motion suite that has the minimum variability above the mean, just because you're picking records that have similar shapes to what your target spectrum is. On the other hand, for the conditional mean spectrum, we actually went all the way and looked at conditional spectra. And this is the process that was developed by Jack Baker. And we actually used his tool that he's published on his website. And we just I expanded it to be able to run many more ground motion suites than a single case. But here in this case, you define your CMS condition at 0.25 seconds, and then the CS, the conditional spectra, define through correlation coefficient the mean about this conditioning point, as well as the variability. And so I'm going to show you plots for these two. The first one is the ground motion suites for the UHS with the minimum variability. These are for the same site, San Francisco, not the airport, just San Francisco, at a VS30 of 270 meters per second. So what you have is, I'm going to start actually on the bottom left figure. All these are spectra. In the very bottom left figure, we're looking at an individual return period of 2,500 years. And what I'm plotting is the Rod D50 of each ground motion pair. So you'll see 40 colorful lines. On top of that, I've plotted in red the target spectrum, which is the UHS for this site and this return period in this case. And then in black, I am plotting the average of the ground motion suites of these 40 Rod D50s that you see here. And for the uniform hazard spectrum, remember, I am selecting records to have the best shape. And so you see that the variability in this case is relatively limited. And you see this value up on the top right figure, where we've got a coefficient of variation that is somewhere between 10% to maybe 20, at most 30. You only have to look up to 2 seconds, because beyond 2 seconds was outside the scope of the period range. On the bottom right, I'm actually plotting all return periods for this case, comparing it to the target UHS and the average of the suites. On the top left, I'm only plotting just the average and the UHS on top of them. It's just kind of good to see where it is when you evaluate ground motion suites, what the spread is, and these different quantities. If we move over to the CMS, it looks slightly different. So repeating on the bottom left, I'm looking at my suite. As you can see, all the spectra are scaled such that they have the same spectral acceleration at the conditioning period, and that value is conditioned to the UHS. So at that point, your spectrum and all the points cross at the same value. And then the variability of that suite is defined by parameters and the model that Jack Baker has developed. And you can see those values on the top right, where you have a much higher variability. But of course, it's localized at the conditioning period. Again, you see the figure on the bottom right is for all the suites. And on the top left, I'm comparing the average to the UHS, because the average on top of the target would be the same, but just to show you the difference between a CMS mean versus a UHS. And then we also, just to complete the academic study, we looked at different variations. So this was beyond the scope of what we then provided to the analysis group, which are the 2 cases that are highlighted in these red boxes. But I wanted to show you just how things got interesting, and we pursued this concept of looking at variability beyond just the target mean. So it really built up a nice data set that we could look at. Here's a comparison of just the overall suites. I find it fascinating because it really shows you the range of ground motions that were used for the analysis by the analysis group. So those are the highlighted in the red boxes. We also did evaluate the pulse content. As I mentioned, several sites were within 10 kilometers of the active fault. And so what we did is we compared what we had in our ground motion suite to the predictive models in this case. And so here we have it, and it's in the report, and it's nicely documented, and then there's a lot more to it. But I'm showing you here for the 4 sites, 4 sites that were selected here, just the comparison of the predictive model to the content of our ground motions. The numbers are at least in a good range. I almost purposely would tell you that we didn't want to make them site specific, so we couldn't really define the number of pulses based on an individual scenario. We really wanted to cover the entire gamut. And so, but there's a lot of nice study that was done on this. And so in summary, we developed 2 suites of ground motions, but each suite consisted of about 200 cases times 40 record pairs. So it was a very wide program, as others have talked about, and the analysis group will tell you tomorrow, that they actually picked certain representative sites based on the different seismicity. Each ground motion was representative of more than just a point, and we're very confident in these wonderful data set that we have developed. I wanted to highlight a thank you to everybody. What I really personally enjoyed as a researcher is just the work and the interaction that we had real time. It wasn't just, it was kind of like these new methods of analysis or doing performance. We collaborated with the other working groups in real time. This really enabled us to just, one is be a lot busier, but be a lot busier throughout the whole project. And this was possible because of these collaborators, the technical advisory committee, as well as the leadership group and the management group. It was really great to feel their interest and participation at every step of the process. And so with that, I wanted to thank you for your attention, and I hope I gave you some colorful slides.
Thank you so much, Silvia. To our attendees, a reminder to please do submit your questions at the Q&A button at the bottom of your screen, and we will field them as we have time. I just wanted to share with our audience as well as with our team, thinking back on the years of work that has been done to condense them into 15-minute, 20-minute, even 50-minute presentations. It's a whirlwind, and to review all this in a relatively short period of time, it's a challenge, but I would like to thank our presenters for meeting that challenge. Okay, so I actually have questions for everyone in this presentation group. So I'm going to ask if you can turn on your video, turn on your mics, and actually turn on your mics when you do address the questions. Silvia, let's start with you. What was the justification for using the time-independent USERF-3 model and not the time-dependent model?
You got me on the one aspect of the project that I was not directly involved with. And so I'm happy to redirect you to the report, because I know that that was addressed in the report. And it was one of the review questions, and we've addressed it, and it will be in the final version of the report.
Thank you.
Mm-hmm.
Farzin, for the loading protocol, does the single loading protocol used replicate the near fault impulse loading as well as the ordinary far field loading? Can you help us address that?
Sure. I touched on this issue during the presentation. Going back to the work that Tara and Chai did at Davis, they compared the impact of a near field loading protocol with a far field loading protocol, and there was not that much difference between them. In our project, we did monotonic tests on the specimens. This is the work that Tara and Kelly can speak better to it than what I can do. And a one direction push can nicely represent what can happen during a near fault pulse. We have to remember that the reason that we're doing these tests is that we want to make sure that our component models can capture the behavior of these cripple balls. Our loading protocol was not designed to do any pre-qualification. So if you think about the type of histories that we have applied to these cripple balls in the lab and the behavior that it shows from our analytical models match very nicely together. So I tried to respond to the question by saying that we didn't need to come up with a near field loading protocol based on the things that we have already done and things that have happened in the past.
Thank you, Farzin. To Tara and Kelly, for the diagonal sheathing during the in-plane cyclic static test, did you experience some out-of-plane torsion in the specimens?
I think that question is directed towards us, since it was in our small component test program. It's a very good question and anticipated, and one might construe it might occur even for other specimens due to the outboard nature of the exterior finish, particularly for unretrofitted specimens, obviously, and even more so for specimens whereby diagonal sheathing is the primary overlay to the bare framing because of the obvious high strength of that specimen. So it's a very good question. However, in our case, we did not experience significant out of plane torsion per se. We might mention though that the specimens were braced and braced with grease rollers to preserve a pure in-plane response. They were greased, to minimize the contribution to the bracing. So we did see that gap between the rollers, which initially present, closed. So there certainly was, admittedly some nominal out of plane movement of the specimen that's anticipated, but we guided it back into place so that we could only look at the in-plane behavior.
Thank you. And then either Kelly or Tara, can you tell us a little bit about any testing for the sill plate anchorage?
Tara, you did most of the variables on that. Do you want to talk first and then I can mention the large component?
Sure, of course. We did not test bare sill on anchorage. The light and retrofitted configurations were very lightly anchored. And in fact, early on in the project, I remember we were torquing those anchors down and we had load cells and we were measuring, just under our hand torque, that we were imposing much more than we might have expected in older construction in terms of resultant axial force on the anchors. It was not our intent to do so we quickly shifted our gears towards minimizing the amount of torque more towards let's say a hand anchored configuration, where we would get we would expect on the order of a few hundred pounds or so of force in the anchor. So we were tracking that, but we were not per se testing the sill plate in the anchor in its own right by pushing the sill plate as you saw the configuration. So we do know though from there certainly is for some of our cases, and I think I showed some of the resulting hysteresis, both in terms of relative displacement of the cripple wall relative drift, as well as the cripple wall total drift. The total drift is meant to be an absolute measurement of the actuator relative to the ground floor, whereas the relative is meant to be, or is actually the displacement of just the cripple wall itself. And for some instances, particularly the high strength specimens, you're attaining some sliding between the sill and the concrete footing. So that's sort of naturally or innately present when you have a very lightly anchored configuration. I don't know if that didn't really directly answer the question. It's just that we didn't test that per se, but we observed that it occurred.
The other variation that you did test, Tara, was the wet set sills.
Of course, yeah. And I didn't speak about the wet set sills. Yeah, thanks for, of course, bringing that up. Yeah. The wet set sills, we didn't see any movement of a sill that was cast in the concrete. We tested a couple of those configurations that clearly preserves the movement of the sill relative to the foundation. It was perfectly adhered to the foundation, remained perfectly adhered, and under the low strength of those particular specimens, which I anticipate for any of our finished specimens, we did not observe any damage to the foundation locally around the ends or at the sill plate itself. So that was a good bond that was preserved, and I would say observed to be a good performing solution.
And very interesting information on that in the reports. That's worth looking
there is,
at.
Yeah, that is summarized in the report. As Grace said, we run short on time and condensing all of this into 15 to 20 minutes.
Yeah. In terms of the large component, we looked at very lightly anchor bolted foundation sill plates in the pre-retrofit condition. And then we looked at FEMA P1100 recommendations for anchorage in the retrofit condition. In neither case was the anchorage really critical in the load path. It did not determine the capacity or the failure mode. We saw in the large component specimen a better performance in terms of less distress and less slip around the anchors than was seen in the small component. So there's certainly a lot of discussion of that in the comparison report.
Thank you.
I should mention for the, sorry, Grace, just one more important point.
Yep.
And that is for the strongest specimens we tested in the small component program, we actually saw fraction of the anchor bolts at very large drift amplitudes. These were in particular for our diagonally sheathed specimens.
Thank you. And I think we have time for one more question. This comes from Bill Graff. What measurements of building periods, structural periods of vibration, of actual older wood frame buildings were done? And what testing of older, aged, or degraded structures or assemblies was done? So two-part question.
Maybe I can start with discussing the deteriorated or older assemblies. And that was something that was discussed quite a bit, and it's completely recognized that deterioration is another variable in the mix with the existing building stock, along with all of the different material variations and things like that. We did not include that in the testing program, although we would have loved to, because there was so much territory that we had to cover with things that were in good condition, that it wasn't practical to also include that. And so when there are questions later about future testing, that would be a very interesting one to pursue. It is not an easy topic to pursue, to figure out what deterioration and what distribution and how you go about accomplishing it. It is a topic all its own, but a wonderful thing to put on the wish list for future research.
Yeah, I would echo Kelly. Oh, I'm sorry. Go ahead.
Go ahead. You can finish on that one. Go ahead.
Okay, sorry. I would just echo Kelly's sentiment. The only hint maybe in the small component program of a little bit of addressing this issue of deterioration was a cross comparison between the tail extension of the stuff running down the face of the foundation compared to, you know, the lack of the presence of that tail. But what was interesting about those specimens where we did extend the tail, that actually is a very difficult configuration to construct. And what we observed is, although we constructed it in a few situations for a few specimens, as soon as we would move those specimens, detachment of that stucco would occur invariably. And so then, you know, then a minor imposition, even a minor imposition of drift at the very low cycles in the protocol would subsequently, you know, almost immediately result in attachment. And so then you're back to, well, you could have just erected this without that extension down the face. It offered very little to the contribution of the strength and stiffness of the specimen, sans that, that small contribution at the early loading stages.
Let me get back to the first component of Bill's question, and that is what measurements of structural building periods of actual older wood frame building or actual wood frame dwellings was done? Was that part of the testing program? Building periods?
No, that was not part of the testing program. We were just operating in a different area.
I think the period one is related to the work that I was doing on the ground motions.
Mm-hmm.
And for me directly, you know, the period I received was from this group. And so I'm pretty sure they're going to talk about this tomorrow. But the period for the ground motions in the analysis is very much dependent on the period of the model that they're doing for the analyses. And I know a lot of work was done, and Evan showed this morning, you know, 2-story buildings and all the different baseline buildings that were used. And so that was part of the study of the properties of these buildings. And I believe that the period comes out of that type of model. But I'm sure Dave will address that tomorrow in more detail.
Thank you so much, Silvia. At this point, we are at the closure of our program, so I'd like to hand it back over to Janelle to take us out and invite us back in tomorrow morning.